Hello again, fellas. So today I have another slew of updates for the AI, and we're just going to dive right in. So again, you can always check it out on the bitbucket down below, and otherwise we have it in the background here. And at some point I'll start running this again. Let's see if it's gonna, let's set it to 100 games, and we're just going to see what averages. Go crazy, little fella. It might hit a bug. There's a bug that's going around that I'll get to. I haven't actually gotten to play with that bug in debugging yet, so at some point I'll run into it and I'll be able to fix it. But basically, there's sometimes it gets an index out of range and I haven't been able to reproduce it more than one time. We'll see about that later. So, what have I been up to over the last several days? Well, I wish I had actually gotten to make the video earlier so you could see this in steps, and I could lie about it, but that's not as exciting. So, over the last, let's see, 4 days, I've been putting quite a bit of time into this off and on, and had several major breakthroughs. So the first major breakthrough was I found another heuristic that works. All of them do not, except for the initial maximize your empty stuff and don't lose. And the latest one that actually does a significant improvement, so we went from about average of 40,000 score, 35,000 score, to an average of 60 to 65k score. That's pretty huge. And so that was achieved with a small heuristic that I'll bring up here. Way down, scoreboard state, go down here a little bit to this guy. And so all we do is we basically want it to, oh, there's that bug. Should have run it in debug so I could see how to get there. Anyway, we want it to choose lower rows over higher rows. So in the previous video, you might go check out the AI again, and you can see that it tends to stack up all the pieces on the right side, and then it sort of builds them up in columns when it doesn't find matches. And this is not good because it limits its ability to match pieces, because you have less exposed pieces that it can attach to. So therefore it has less opportunities to match, and given that's the only other heuristic working at the moment, severe drawbacks to just stacking it on top of each other. So this heuristic tells it that it should spread them out on the bottom before it starts adding columns. And like I said, that gave it about a 50 to 80% jump in its score. It's pretty gigantic. And so that was the first exciting change that I kind of wish I had made a video on, but it also wouldn't have been that big of a video. The next thing, so that was our first major score bump, and that's about the score that we're getting now. You can see it on the screen there, it's 55k. Sometimes it gets 130, sometimes it still gets 18 if it gets particularly unlucky. Anyway, so the next thing, let me bring up my notes here. Bring my notes up. Alright, so the next thing that we were able to do was, I was getting ready for multithreading and multiprocessing. In order to deal with that, I needed to separate move 1 from move 2. Because move 2 and all the moves that come after it are the ones that we actually want to split into threads and stuff, but the move 1s, there's no reason to. So I wanted to make threads for each of these initial move 1s, and let the move 2s branch off of those, and then they can split among the processors and do their thing. What ended up happening as a result is by splitting search moves and search move from each other, I moved the creation of this board right here outside of the move to loop. Now that is a big deal, and same with this. This is outside of the loop. So in essence, we create a total of only 23 boards or so. And that's a pretty big... Actually, I can probably move this one out and save another few boards. I should look at that before I do it, but theoretically I can move that one out and save another 20 boards or so. But basically what was going on is in the loop, in the inside of that previous loop, I was making about 450 boards out of the 480 extra. And so, you know, that huge factor of 9 out of 10 boards being completely unnecessary to build. Added all that garbage collection and all that initialization, all that memory grabbing, memory allocation in there, and it made it very inefficient. And so just that little bit of loop unrolling accidentally gave me a 2x speed increase, which was pretty massive. So we went from about 3,500 board states a second to about 5,500 to 7,500 depending. I don't quite remember, but basically that's pretty big leap at the time. That's our first 2x speed increase. And so that was the next big exciting thing that I wanted to talk about, but I just couldn't get around to it. I had band practice last couple of days, and yeah. So then I spent the next day, probably Thursday, doing multi-threading. And I thought this would give me a 4x speed increase, and it actually didn't, which was a pretty interesting result. What ended up happening was basically because I was creating 88 threads or 150 threads or whatever it was a second, and deleting them and creating them and deleting them, it was slowing everything down, and it actually cost me most of my speed gain. It brought me back down 50% of my moves. It was back to like 10. It was back to 6 moves a second as compared to 11 or 12. So it was a pretty big loss, and so that was a little bit obnoxious. So then I had read that maybe multiprocessing would treat me better. So multiprocessing is basically the same as multi-threading, except for I'm spawning new processes instead of splitting the same process into different chunks. So you spawn a new process to go calculate some stuff and then come back to you with the answer. That was actually even slower. Now, again, same kind of issue where you're asking the OS to go do some special crap for you, and so you gotta wait for all these calls to happen, and it's allocating memory for your program, and then you kill the program, and then you start the program, blah blah. And so I think that this code will be useful later, when that overhead is minimized and spread out over a second or two, whereas right now it's got so much overhead for not very much gain. And so anyway, so those are implemented. I can show you them right here. Bubba-dub, bubba-doo. And multiprocessing was particularly obnoxious to program because there's a pitfall in it where if you do not have your main guard right there, you actually fork your computer to death unless you have a nice little batch file to go kill all the processes. Well, I didn't write that yet, so now I have a little batch file that says go kill all of the Python, don't let it get away, kind of a thing, and that's great. So anyway, that was a thing, and like I said, none of the work was worth it yet, but I think it will be worth it here in next week sometime once I actually get to move 3s and need that 4x to make it even somewhat practical. But another major breakthrough happened today. So a few days ago, and maybe even the previous video, I had said I wanted to refactor the entire game board. Now, I don't know if you noticed how fast everything was running down there, but I'm pretty darn happy about it. So basically, the previous top speed I could get on the last video was, I think, 4 moves a second. So 2,000, 2,500-ish board states per second. Then when I got that first loop unroll, we got up to about 6 moves, so it was in the 3,500 range, or maybe it was a little faster than that, I don't remember. And now, with the refactoring and a few other little things, we're up to 38,000 moves, 38,000 board states, or about 30-something moves per second. Now that is huge. That's that's our first order of magnitude that we've actually achieved, and that's very promising. That gives us the leverage that once we get another order of magnitude from something like pruning of different kinds, that's probably enough to get us there. And if we wanted to search even deeper, I don't know if I remember. I don't remember if I mentioned this last time, but along with multiprocessing, I had considered using the GPU. Now that's going to be one of the last steps I do, because I only have NVIDIA in one of my computers. So the computer I'm sitting at now is the only one I can actually work on what's called CUDA, which is a set of libraries that they happen to also have for Python, where you can wrap some subset of code and send it to the graphics processor and let it crank away on that. Now, that, supposedly, is supposed to give you a 19x to 2000x speedup. So if we're pessimistic and we say, pessimistic but still pretty optimistic, and we can say get 1 order of magnitude out of the graphics processor, that's pretty awesome. That's a free order of magnitude. That basically gets us as fast as I ever wanted to go. And we can stack that on top and probably go even faster and just see what we can actually get away with. If I can have it beat the top players and do it in 2 seconds, that's pretty awesome. But, let's not get ahead of ourselves. The first thing we want to do is actually get it beating top players. So the whole refactoring thing is what I ended up finishing today. As you can see on screen, there's still a bug sitting there that I got to go debug. But aside from that, it's all working fine as far as I can tell. I had some custom moves on it. I played a bunch of random games on it and that kind of thing. It seems to be operating pretty much the way it should. So again, theoretically, we're God, I wish I quite knew what that bug was. I kind of wish I knew what that was all about, but we'll get there. So yeah, the whole thing going on here is that now we're up to almost 40k board states a second, and that's a pretty real amount. You multiply that by 4 for your threading or your Python multiprocessing, you're up to 160k. That means even when we get to the abysmal move 10-piece combinator things where it increases by 3 orders of magnitude without any pruning, that's 500,000 board states. But we can now do that in 3 to 4 seconds, which is... that's just fine for testing. That's almost as low as I wanted it as a human. And once we add pruning and prune off 80% of those moves because they suck, we should be golden. So I think that's the major updates. So we have multithreading available, multiprocessing available. We have an awesome heuristic that increased the score a whole bunch. We have the complete refactoring of the game board, which gave us an order of magnitude speed up, roughly. That's pretty awesome. And, when combined with the loop unrolling. And, yeah, pretty good. So, the next couple of steps, as I look at my notes here, bring them a little bit over here so I can pretend I'm looking at the camera. Let's see, the next steps are, so we actually want to implement move 3. That's going to be a little scary because, again, once we get to those top moves, I suspect it's going to go real slow. So I think at the same time that I implement that, I'm going to have some... So the problem is I have to implement that, test it, and then hold those scores around to test against pruning. Because if I don't hold those scores around, then what's going to happen is when I prune, I don't know if I start getting worse scores because of the pruning, then even though we're going faster, there's a good chance that we're making our score worse. So I need to make sure that I prune the right subtrees so that when we're searching, it's worth it. So that's problem 1, is getting move 3 up and running, which shouldn't be too hard, and then starting to prune it, which might be a little more difficult. So the way I'm actually going to be pruning, or at least choosing the best move for move 3, is we're going to look at average values, is what I'm leaning towards right now. Since I'm not using actual board points, since I don't care about game points and all I care about are empty spaces and how much we're filling the bottom as opposed to other spots, then I think if I take the average board score for the whole of each move 3, then what we should get is the best moves for minimizing board state. Now, currently the heuristic that I was talking about last time, I think, about matching pieces didn't work very well. Now I kind of want to retest it, but it's actually pretty pointless as soon as we start searching move 3. Because what's going to happen in move 3 is it's going to test every possible combination of pieces, which means that all of those pieces that could match or could create a 3-buy for us later will actually be tested against. And what will happen is that will increase the average score of whoever gets the most predicted empty spaces. And so wherever the computer thinks it's going to get the most empty spaces is what's going to hedge towards. And then it might start looking like it's playing like a human. It might start correcting some of those moves where you think it should flip it backwards or whatever. And once it starts doing that, I think that we're going to be real close to the end of that part of the task. I think that we're going to do a few prunes and see if we can't get to move 4. Because again, the more that it searches and the more it has informing that average, the closer we're going to be to having it get those top scores like we want it to. But all things in time. So I guess that's pretty much it for where we're at. Is we're going to work on move 3 and get a prune or 2 in there. And I'll probably see you in 2 days-ish. I'll probably have that uploaded on Monday for another large update. But who knows? Maybe I'll get that figured out tomorrow, and I'll be too excited not to come post and rant about it. So until then, happy programming, and I'll see you later.